this is how you can think of the UTXO model. When you have an input, it always must be spent. It's always unique. You cannot spend an input more than once. Unlike cash, I guess, like the cashier could spend it in other places, but in the UTXO model, it can be only spent once. Hey guys, so today we're going to be talking about palm staking on the UTXO model. So over the last year or so, I worked on implementing a native token staking platform on Cardano. And as you know, Cardano and Ergo are very similar in terms of how their contracts work, and they all share the UTXO model. So I'll try to keep this as easy to understand as possible so everyone can understand. So we have some existing implementations of staking already. So if you guys don't know, over the last cycle, DeFi summer, we had Sushi Swap and Pancake Swap. And for really anyone new here, Pancake Swap was like how Solana is today. Like they had all the memes and they were going crazy with all the meme coins, all the launches, and staking with those meme coins. And before Pancake Swap, we had a Sushi Swap, which really was a Uniswap clone, but they actually did some research and they were the first ones to implement this the modern native token staking or ERC20 staking. So Sushi Swap had this staking, which really is to incentivize people, right? Because staking makes people hold their tokens, right? So it kind of stabilizes price movements. And yeah, Sushi Swap pioneered this, and then we got Pancake Swap, which basically copied it and made some improvements and really brought it to the mass users, right? Tons of people were just making meme coins and having staking with it. So, you don't sell those meme coins and kind of like a inflation and a Ponzi scheme and so on. So let's have a refresher. So what is the account model and what is the UTXO model, right? So the account model is all right, let's start with UTXO. The slide is here. So what are UTXOs? UTXOs were pioneered by Bitcoin, right? That's how they started their entire system. So UTXOs stand for unspent transaction outputs. And the out it's basically the output of the previous transaction you did. So when you submit a transaction, you have a bunch of metadata, right? You have what went into the transaction and what came out of the transaction, and the outputs of this transaction are referred to as UTXOs. And the transaction model really is an exact digital analogy to cash. So let's say I have a $10 bill and I want to pay for $6 coffee. It's probably $8 now, no inflation. And if I want to pay for $6 of coffee with my $10 bill, I can't just rip the bill in half, right? I have to spend the entire $10 bill. So what do? I give the cashier my entire bill, and that's it. They have the bill. They're not going to rip it in half or anything, right? It's just gone. But they're going to give me back $4, right? And this $4 is completely new, right? It's not the original bill, it's just completely new. The $10 I had, it's gone. So this is how you can think of the UTXO model. When you have an input, it always must be spent. It's always unique. You cannot spend an input more than once. Unlike cash, I guess, like the cashier could spend it in other places, but in the UTXO model, it can be only spent once. And my another analogy that I like is with the old-fashioned piggy banks, right? So you would have savings in a piggy bank, and if you ever wanted to spend it, you would have to smash it open, right? It's like a one-time thing. So you can also think it of that, right? I have $10 in my piggy bank. The piggy bank is the UTXO, and that's like the input, right? And then if I want to actually spend it, I would smash the piggy bank open, and it's gone, right? Just one time. So that's really a brief overview of the UTXO model, and Cardano and Ergo both make use of this. So what's the account model? Account model is really the newer model, and it was pioneered by Ethereum. And account model really is analogous to your bank account, where you just have a list of transactions saying that maybe $10 was deposited and you're spending $1, and you have a list of transaction history, right? So addresses are seen as accounts, and you just have a direct tally of balance. And the thing with this, and I think of it as a problem, is that you need global state, right? So you need to know the history of everything from the start, right? When the account got funded to how much you have now, to know how much you have at this moment, right? You have to do, some calculations, right? Some balance add, balance deductions, and so on. So, but this is overall how the account model works, and it is also quite popular, right? All the Ethereum forks use that, and Solana uses that, and all the newer blockchains also use that. Um, for those of you following Cardano, they have a new blockchain called Midnight that they're probably going to launch, next quarter or so. And Midnight uses a hybrid of account model and UTXO, so it's quite popular. So let's talk about the advantage of account model in the context of this staking. So staking is more analogous to a client-server interaction. So what that means is that a server is really just a computer that never turns off, right? It's always running in the background. And client is really the people who hit that server, right? You need to talk to that server to do something. So, for example, if you're logging into your email account, right, you're accessing a server which, holds all your emails and all, right? And you're the client, you're trying to log in from your laptop, right? So that's a client server interaction. So staking is similar to this interaction where the stakers are the clients, right? And they deposit their tokens to a contract. And this contract, you can think of it as like a server in the sense that the contract has to manage all the global state, right? It has to track the balance so it knows how much rewards that you get, right? Because rewards are a function of how much tokens you deposit and how long you have deposited them for. So Solidity is the smart contract, a very popular smart contract language that runs on this account model. So Solidity is perfect, right? It has a single authoritative contract storage, right? So you have something called a map, and a map is a very basic data structure that you have a key. So a key is like the user, like your user, your wallet address, right? So and if you access the data within that wallet address, you have a bunch of data, right? Like how much they have deposited in the contract, and how long they had the tokens on, and all sorts of useful information. Perfect for this. And then this doesn't translate well to something in the UTXO model. So for UTXO contracts, you have a single UTXO, right? And each UTXO, you can think of it as its own entity. So in UTXO has its each UTXO can have its own contract. So a contract's state really is with respect to the UTXO it's inside of. So a UTXO has this bottleneck, right? You can't just store infinite data in it, right? The UTXO, you have a size limit, and you also have a broader transaction size limit because you can argue that, hey, why don't you have like a bunch of UTXOs this single UTXOs interact with, right? So you can have like a bunch of data, right? So if a UTXO data size limit's like 4 kilobytes, you can be like, okay, why don't we just do like 1,000 UTXOs, right? Why not? Why not make it like 4 gigabytes or something, right? No, that's not possible because you have your bottleneck by transaction size limits. You can only deal with a specific amount of UTXOs per transaction. And then on top of that, you also got the block size limit, right? So you can only have a certain amount of transactions per block. So a lot of bottlenecks here. So how can we move on with this, right? Like it almost seems impossible to bring something that needs such a large global state because remember, this might translate to like 10 users, 100 users. But how are we going to scale to like 10,000 users, right? Because all each user has are going to have some size of data, right? That's not going to scale. So how do we do this? So, I had to rethink staking on the UTXO model. So, data stored for the global variables, so for like all sorts of staking calculations, they need to be bound to a constant size limit. You can't have it scale with the amount of users, right? So you can't be like, okay, one user is like 1 GB of data, right? It's 10,000 users is 10,000 gigabytes. Like we can't scale like that. It has to be one user is like 1 GB of data. A million users is still 1 GB of data, right? How can we make that happen? It has to be constant. So a clear solution which several projects on Cardano and Ergo follow. So I think what was it? Ergo something or the people behind Crux Finance. I'm forgetting their name. I think they're shut down now, but they pioneered a staking model, and then a bunch of Cardano projects have their own staking. So what do they do? So they have some sort of position or UTXO or NFT that you can think of, which indicates a share of how much they have staked, right? So let's say you stake a certain amount of tokens, you'll get back like a unique token saying that, hey, this person staked like 100 tokens on the platform at this time, right? So if you ever want to claim that stake back, make an update, you have to deposit that unique token you got back into the contract, right? And this is pretty straightforward and well-known solution to this problem. However, this was not ideal for Zengate's purpose because of legal conflicts. The problem is that you can have derivative markets of something like a position token because I can take my position token and I can be like, okay, I don't want to be in this anymore, but I don't want to. You don't want to lose like that accumulation of rewards, right? Like maybe like the longer you stake, the faster you earn rewards or something, right? It keeps compounding. So maybe I sell it to someone else, or just give it to someone else, right? Or what if so you create these derivative markets, and it's a conflict from a legal standpoint. I don't know why, but it is what it is. It's a very gray area in general, unfortunately. So so I thought of this data structure called a Merkle tree, and this was absolutely perfect. So on Ergo, you have the AVL tree, and it's quite similar, so it can just translate to Ergo. Also, what's actually really interesting is that the Merkle tree data structure is something that was just implemented at a contract level on Cardano. However, on ErgoScript, you have a AVL tree as like a native data structure within the language. So what that means is that basically you can trust the data structure on Ergo more because like the core team, so basically Kushti made the implementation like in the compiler itself, right? So it's not like a third party code that you're trusting to be correct, which is the case on Cardano. So let's see what is a Merkle tree because I honestly barely knew about it until I did this. All right, so a Merkle tree is a tree-based data structure, and a tree-based data structure you can really think of it having like a root at the top, and it has branches pointing to more roots, right? So you can kind of see that data structure in the diagram behind me and the boxes, right? They're called nodes. So you have like one like root node, like it's the main node on top. Then you have those lines are called branches, and then you have like another node that's like called branches. That those are called like they're like intermediary nodes, and all the way at the bottom you can see a bunch of nodes, right? Like the final nodes, those are called the leaves. Or that's just a very well-known data structure in computer science. So a Merkle tree is a variant of this data structure, and it's made by hashing hashes of data. So I know that's confusing, so let's break that down. So behind me, you can see that you have a block of data, right? Like a block of files. So A dot text, B dot text, C dot text, D dot text, and you hash this block of data. And hashing really means is that you take data of any size and you convert it into a fixed sized string of a certain data size, right? So in this or in well in most cases it's always 32 bytes of data. So it's like a string of 64 characters. And the cool part about this, which is really important in security context, is that it's irreversible. So if you have this fixed size string, you can't get the data back. It's impossible. But that's beyond the scope of this presentation. So again, you have a data and you transform it into a fixed size unique string. So you can see a dot text has a hash h1z2, b dot text has its own hash, and so on. So how does this translate to a Merkle tree? So look at the tree behind me. All the way at the bottom, the leaf nodes, you can see that we brought those hashes over, right? The H1Z2Y 77A and so on, right? So those are the hashes brought to the node and they're at the bottom. So now you look at the left side, the bottom left side of the tree. So H1, so we take the H1Z2 Y 7FA. I can't read it from here. And so those are the hashes for a.text.b.text, right? So we take those hashes and we concatenate them, we put them together, and we take the hash of that. So the hash of that you can see is right above those two, right? So it's U67R, right, on the left side. And again, we do this exact thing on the right side. So for C.text and D.text, and we get a hash. Now those like hashes in the middle, again, we take them, we concatenate them, and we get the hash. And that final hash is called the root hash. So why this is really cool is because you can find differences between two states, so meaning like two different trees. So if you made any modifications, you can find the difference between them like really fast because think of it logically, right? If you have two pieces of data, what do you have to do? You have to iterate through them, right? Like one like bit at a time, like the smallest like unit of difference, right? You have to iterate through them. So, if there's like a million pieces of like units of data, you have to make at least like at most a million iterations, right? It doesn't scale. So with this, it's a lot faster, right? It's like the log of a million, maybe that's like what, like 1,000 or 10,000, I don't know, but it's a lot significantly faster, right? So let me explain this further. So you can see that we had the text files, right? And we changed the contents of c.text. And what does that do? We got a new hash. So you can see 4W12, right? So on the right side of the Merkle tree, you can see that all the way at the bottom, that changed, right? It's in yellow. And now since that changed, the hash above it, which is remember made by concatenating the hash of c.text and d.text, that also changed, right? And since that changed, the root hash also changed. So you can see here that when you traverse the tree, you first check the left side and you're like, oh, the left side's exactly the same. So you know that a.text and b.text is completely unchanged. But then you go to the right side and you can see that okay, d.text isn't changed, right? At the bottom right, it's still the same. So then you know really quickly that c.text is changed. Like so it's a really clever data structure and it actually powers so much of the modern infrastructure. You just don't know it. But that's a quick introduction to a Merkle tree. So yeah, you can see here like the comparisons made, right? So on the left side was the original tree, and the right side is the tree with the C dot text changed. So you can see we just make three comparisons, right? So this scales really well. Now, what we actually use for the staking is something called the Merkle Patricia Trie, and what this is basically an optimized version of the Merkle tree. So a tree really is a is it just you can think of it as like a key value map, right? Indexed by like the keys nibble. So it's just like a bunch of characters, like ASCII characters, and that's what a trie is. And Patricia is just an optimization of the path, right? So it's a very optimized structure. So you make even less. So in the previous slide, we made like three traversals, right? So this makes it even smaller, like maybe like one or two. And then Merkle, is from what we discussed before. And then the proof is the path of nodes that you traversed, right? So in the previous slide, we traversed through like three nodes. So that's like the proof. You can think of it as that. And then proving, right? What is the action of proving? So you have the inputs of the known root hash, right? So the hash all the way at the top, you have that. And then you provide the proof. So you provide that path. And then you provide the key and the claimed value, right? So you walk through that from the root node to all the to until you get to the key, right? You walk through the tree, and then once you reach to the value, you stop, and then you compute the root hashes from that traversal, right? You can do that same hashing from the scratch, and then you compare it. Hey, is the thing I computed, does it match what I already know? And if yes, then you know that everything's correct, like no one's messing with anything, right? And yeah, so membership is proven when the computed root equals the known root, and the known root is what you passed in. So let's talk about how this integrates into staking. So client balances, right, are stored in this Trie-based data structure. And on-chain, so in the contracts itself, only the root hash is stored. And remember, the root hash is a fixed size string of 32 bytes, right? Because it's a hash. And that answers the problem in the, we saw a couple slides back where we want like one user to be like, say, 1 GB of data, and we want a million users to still be that 1 GB of data, right? So it's constant. So in this case, it's always a constant 32 bytes, right? Which is incredibly tiny. So it's always this number, even if we have a million clients, which is really cool. And thanks to that, the Merkle tree diagram I explained, right? It's hashes of hashes of hashes and so on. So anytime any insertions or updates done, the contract does verification, right? So as I explained in the previous slide, you have a proof and you have the known root hash. So you provide the proof and the known root hash. And what does the contract do? The contract only does computing, right? It only does verification. It all the doesn't need to do all the data storage or anything, right? You provide it the exact data that it needs, the least amount of data it needs to actually prove what you're doing is correct and you're not providing false information. So, and remember, after all of this is done, so if there's any like mutations done to the state, so meaning like if you added more stake or you did a claim or you did a withdrawal, that's a mutation, right? Um, the only thing that changes is the root hash, right? So it's always that constant size length. And when these updates and claims happen, like you're providing the proof, right? So I guess the downside of this is that you have the overhead of you have to store this data somewhere. It's not magic, right? So you have to store the data in your own server, right? It's called the off chain. So you have to store the data. You're responsible for storing the data. In Solidity, you can just throw it on the blockchain and you just make sure like the EVM nodes, right? The Ethereum nodes, the heavy 2 or 3 terabytes, 6 terabytes nodes, right? That stores all of that, right? So you just worry about that. But on the Ergo sense, you are storing the data. So really the final slide here is improvements made to the original protocol, right? So the original contracts was short-lived and static. So like I said, it was originally meant for like things like meme coins, right? So where you just don't want people to sell, right? You don't really think about long term. And the problem with this was it's very it was very static. So you have one emission rate for the whole program. So what I also added to the staking contract, the protocol itself, not the UTXO implementation, is I made the emissions very dynamic. So like every epoch, so for example, on Palm staking, every week people can claim their rewards. This emission amount can fluctuate without, having to redeploy the contract or get people to migrate. And this is really cool because a dynamic protocol allows us to easily curb any excess inflation, or it incentivizes staking during, like steep price movements. So it allows us for more of a fine-grained control rather than so we actually react to how the economy is doing, right? I mean, you saw yesterday that things went crazy. So maybe during a time like that, you want to incentivize people to hold, right? So maybe we'll tell them, okay, we can increase inflation so that people hold on to their palms of selling it on the market just for no reason, right? When everything's going crazy, right? So then people might not sell because they'll say, hey, like I can just put it in the contract. I believe in Palm. I believe in this token's future, right? I believe in crypto. So like maybe in next week, you're not gonna the tariffs are gonna be reversed, and we won't have an issue. So maybe I want to hold my Palm and make some more Palm and money instead of selling, right? So the dynamic protocol really allows for this. Thanks for tuning in, guys.